that happens here. So I'm going to tell you about some work that, ACL2 is a prover, a third generation or fourth generation prover. Jay can tell you, that he and Bob started back in, many years ago. So we interact very closely with industry and actually with this company Centaur, which is a wholly owned subsidiary of VIA Technology, and they build x86, design and manufacture x86 microprocessors. And so that's the hardware stuff we're working on. Why are we working on things like that? Well, about 10 years ago, I just got frustrated with stupid hardware models and just didn't want to work on anything unless it was commercial. And I just about given up and quit because no one wanted to use formal methods. But then this company called me and said, well, can you come talk to us? And I went out and talked to them. And I talked to them for 30 minutes. And I didn't know who the people were there. There were just 3 people in this conference room, bigger than this, twice as big as this, 100 chairs in. And I said, well, that's what I do. And then at the end of the meeting, the president just asked me, his name is Glenn Henry, well, what do you need? And I said, well, I'd like a big computer and, an office and so forth. And this was on Thursday. And he said, okay, fine. And so I left, and like most times you interact with a company, you don't hear from them, whatever. So the next day I got a call on Friday, and they said that my office was ready. And that my machine, which was a 128 gigabyte machine, which was a pretty big machine 8 years ago, would be there on Tuesday. And the last thing the president told me was, don't talk to anybody. Because, they didn't want me to waste any engineers' time. But I've gotten kicked around long enough at IBM to know better than to go talk to engineers, because that just pisses their managers off. So every time I snuck in and talked to an engineer, I would tell that engineer that I will pay them back double and I will work for them and do things that they need done, and I'll do their junk work, if you will, as long as they'll answer a few of my questions. And so, and that's how we started out, myself and a student. And then after we had an initial success, about 6 or 8 months later, and the company got behind it and invested in it, and they've got more formal methods per engineer of any company in the world, as far as I'm concerned. And it's they believe in the technology, and they've lined up money and resources behind it. Okay, so the people, these are either students or ex-students of Jay's and mine, and except for this, I'm Slobodo, she's the manager there, and you can contact her here if you wish to get some information, and she's been the manager there for the last 6 years. So what am I going to tell you about? Well, the hardware verification work we're doing, the software verification work that we're doing, and then I'm going to conclude, and if I don't get yanked off the stage first. Okay, so introduction. So we're trying to accurately model commercial size systems. I don't want to work on any toy examples. And what you find when your verification tools get really good is you don't want to work on them, but you'll find bugs right away in simple things that students or a few people put together. When 100 people are working on a design and they've been working on the same design for many years, it's actually very good. It's very clean. It doesn't have very many bugs in it, and they're really interested in the bugs because they're really hard to find then, because they've got 500 person years of effort they've already placed against it or more, and so it's a serious undertaking. So we're trying to verify properties of commercial designs, and specifically we're working on x86, but we also there's another group that works on Spark, and there are other groups that work that do some work with our tools at AMD and Intel and Rockwell Collins and so on. We've developed an x86 model that we can use to prove it's both it's a target specification for the chip verification work that we work on, but it's also the compile to specification for computer programs. And so I'm going to talk about how we prove programs correct. And simply what we do is we just take the output bits of the compiler, we jam them in our model, and then we do mechanical proofs. So how do we do those? Well, we use the ACL2 theorem proving environment. We're constantly trying to improve that. The talk that Jay's going to give here in 20 minutes or so is one step of that. So we're constantly, I'm always out trying to use the prover on something that's ridiculously too big and should never, be attempted, but we just keep banging on it, and, somehow Jay and Matt or whomever get in there and fix something, or even I occasionally try to and manage to extend the system. Because they have safe mechanisms they built into the system that allow you to extend the system, and then if you prove that extension correct, well, then it gets integrated into the automatic procedures. And so you can, you're still relying on the core and Jay and Matt to do their thing. And so we're just always working on commercial size problems. So our hardware objective, x86, software objective, proving programs that sit and run the x86 binary. That's where it is. And note there are others like NICTA, L4 microkernel verification project, x86 effort at Harvard, FreeBSD at Cambridge on the ARM models, all kinds of other work. I'm not going to talk about them. They're all great things and urge you to them. Our ecosystem, it's just not the 10 or so people we have at the university. We also have close relationships with the companies I've already mentioned. Our closest is Centaur and Oracle, where at Centaur we have about 4 people or 5 people we work with regularly, and Oracle now has grown beyond that. They have about 6 or so people using our tools. We also work with these other companies and organizations. And so, of course, our research involves developing the core technologies, extending what we can actually do with the tools, applying these in different domains, and then their commercial use. Okay. So this is a timeline. Now I didn't join until right in here, but Jay and Bob started back here in 71 or 72 in Edinburgh, actually. That's where they met, and then they did some things, and then came to UT in Austin, started to have students, and then students went crazy doing all kinds of crazy things. We ran out of space over here. There have been other things in here, but I didn't want to restructure the whole chart. It's just, I don't know. They're just all of these are, each one of them, the stories in themselves. They're big libraries that you can check out called books and if you download the ACL2 system and all the corpus of previously created models and their proof, associated proof material, then you can rerun all those proofs and check them, and then you could take them and modify them or extend them or whatever you wanted to do. So we've been at this a while. That's the point. I've only been doing it for 30 plus years, but Jay can stay to 40 plus. Okay, hardware verification. We're looking at this VIA part. Full x86 64 compatible, 28 nanometer of implementation, 220 plus million transistors, has built-in ASDS, SHA, all kinds of stuff, random number generators. Those are extra things that don't appear in all x86 designs. Runs over 40 different operating systems, tens of thousands of things, applications, 5 different VMs that run on it. Has a built-in security coprocessor. You can't see it in there, but somewhere in there, and I can find it for you, but I would need a magnifying glass. Is a second processor. There's a subprocessor. That's very common in today's designs. So there's the 4 cores. This is cache, and this is more cache, and then there's a bunch of microcode and other things in there. So where do the formal methods get in the fight? Well, there's concept. You drive this down into register transfer level kind of design. That eventually gets reified into transistor level and then pushed all the way down into the layout. And then, of course, from the layout, you make what they call release interchange tapes that, and you send it off to fab. Currently, the fab is TSMC, Taiwan. So everything over here, these purple, are what formal methods are being used to help with reverse engineering, doing algorithm development. We have an RTL browser. You can browse the entire x86 RTL. That's a little over 700,000 lines of code. It's been ingested, processed by our system, regurgitated, and put in a form that's easier to read and give it back to you. That's just helpful when you're looking for things. A linter, meaning it just cleans it. In fact, the designers at Centaur are not allowed to check in the design, meaning put it back in the database unless it runs all of the tools that we have developed to check, because our tools are much more thorough than the Verilog, the 4 different Verilog simulators that they use. We always catch bugs even after they've used all 4 simulators, just syntactically. It's just amazing how bad these tools are. We do proofs, we do microcode proofs, we do equivalence checking, we do signal mapping. These are all things that are being done, and it doesn't show, yeah, it's got microcode proofs. But anyway, this is a pretty complicated device. The verification framework, at the bottom we have ACL2. We have various books that we've developed over the years. These are extensions to the system, like I was mentioning earlier. For instance, a symbolic simulation package called GL. That's for generalized in the logic. You know, there's links to satisfiability solvers. If we do that, then we check and we verify the results of the satisfiability thing. The solvers emit now a format that we developed called DRAT trim, and then we check that the DRAT trim, that the SAT results or the unsat results are correct. So we're very careful about our tools. Then the Centaur people start stacking up models on top of it, like the hardware model. As I said, that's mechanically translated from about 1.1 million lines of Verilog chipset and part. And then, you know, microcode, well, that's actually part of the hardware. And then there's lots and lots of regression tools. And then, of course, there are these extra tools to help you drive through a design of that size, because just knowing where you are, what you're looking at, and so forth, these are hard problems when you get something this big. Now, what gets done there? Okay, well, designers write specifications kind of up here in this top level, here. You know, I don't know, brownish box or whatever is meant to be that. The microcode modeling is done over here. That's where the hardware is taken, and then it's proven equivalent to some, you know, sort of, I'll say a little bit more abstract, but it's bit for bit exact model. And then you see how the microcode affects it. And of course, you're going to check that against the x86 model. All this sort of green stuff, which again, this projector's not, so the contrast isn't so high as it is on the way it looks on my laptop. But there are proofs through here, also proofs comparing this symbolic microcode model down to the actual model. All of this stuff is represented in Verilog, the entire design. And, you know, and then there's the process that shows that these go down to the transistor level and eventually the chip. And our tools are also used based on ACL2 to check the transistor level design. We check, you know, millions of collections of transistors, and show that the transistors implement the necessary finite state machines. Not for the entire chip, but for you know, fairly large pieces of it. Just to give you an idea of one thing that's being done on the hardware side is checking the microcode. Microcode is, you can issue up to 3 microcode instructions per cycle. What happens is instructions come in, they're cracked, broken into pieces. Pieces are then split into these little instructions that are 150 bits wide that tell the underlying RISC processor what to do. And so, you know, if it's more than 2 or 3 of those, if it's only 1 or 2, and sometimes 3, they're looked up in a ROM. Otherwise, you go to a special kind of decoded ROM for the commonly used instructions, but for the complicated ones like call gate or interrupts or other kinds of things, there's over 30,000 words of 150 bits each that describe what the machine should do under these cases. And so and you know, so this chart here is just meant to show that a regular, you know, an x86 instruction that you might look at that comes out of a compiler, well, that bit pattern, it takes on into the front end, it's busted up into these micro ops, and it shows 3 here, which might just happen automatically from the decoding logic, and if not, again, it accesses the ROM, and that just streams more of these micro ops into the core execution units of the machine. And then these things are, you know, calculate the results of what the instructions are, and then puts the results back and so forth, and the process repeats. This is an out of order core, which means that you issue in order, meaning the instructions you put into this wad of stuff in the order that they came, but then it may choose to reorder them depending on the resources availabilities, both of the operands and of the execution units. And that happens dynamically as the part runs. Just to give you an idea of how the microcode proofs have been done, is that this model over here, which is sort of the Verilog model, an equivalent model was built over here in our formal thing. Most of that's generated mechanically and then proofed or checked equivalent to this part of the model mechanically. This being sort of the same units that you saw here. And so these are the reservation state, the reorder buffer, the memory order buffer, register file, and so forth, and a fair amount of complexity and all this stuff. So this part will, you know, kind of this piece here is shown equivalent to that piece, and then up at the top you have the ROM, and the things come in. The ROMs are actually the instructions are actually more compact than in the ROM, and then they're exploded. And so the translator turns them into, you know, these wider instructions that the machine actually understands. And then that, you know, this micro translator model is produced by a symbolic simulation of the actual translator. And then you can go and you know, check the microcode programs by proof, which is what we do in this kind of classic core style proofs. say that. So, Tony's one of my heroes. In fact, he even made fun of me 30 years ago, Mark Oberdorf, and made a, I don't know, just, it was something the directors did. They picked on a couple of the dumber ones that were there, and Tony got me for some reason. We'll have to ask him why. This process is very automated. It has to be because it runs every day. Automatic translation to 1.1 million lines of Verilog, so suitable for verification. Nightly regressions, all proofs runs on hundreds of machines because there's thousands of proofs. Errors introduced yesterday are addressed today. If there's an error, then the designers are contacted. They get into a discussion and see whether it really is an error, or was it a specification problem, or was it a proof problem, or who knows what. Okay. So many design elements are subjected to verification: arithmetic, floating point, media functions, transistor level circuits, clock trees, and microcode. So for instance, a string decompression algorithm of about 800 instructions, several loops, was recently verified by Honest Lobodova. Very difficult thing to do. The ROM inside that has all this stuff, the microcode thing, is itself compressed, and one of the first things it has to do is uncompress itself, and that's what this program was. And so before you even get to execute the first instruction, many thousands of clock ticks or cycles have been run because it's building itself, or in other words, inside. Okay, software verification. In 11 minutes, I guess. Yeah. I'm supposed to settle down. All right, so this is a classic, kind of diagram that you see when you say you're going to specify what software does, right? You say, oh, well, you're going to show the state of the machine. There are a few registers, an instruction pointer, and flags, and then you find, and the memory, of course, and then you have this next state set function that tells you in one fell swoop what the instruction does and what the updates will be to the memory, the registers, and the flags. And we love this. It's beautiful. It's all that kind of stuff. And but our model also includes the supervisor level stuff. The machine code, of course, you've got to you're working from the binary, right? And we use it to develop our trustworthy programs. And note this is a build tube, and as I said, specification for x86 vendors and a compile tube for the user spec. But this picture is a joke. Okay, the picture, it looks more like that. All right. Right here are the register files. That's all. That's the register file right there. Then you've got segment registers. You've got stack pointer, other kinds of things. You've got floating point registers, which are mostly deprecated. You've got the SSC registers. All this stuff down here. You've got the memory, but that's even not close to enough. You've got all the control registers, and one of those control registers, like number 3, is the base for right there. Again, it's used for the base of the decoding. Where the various descriptor tables sit in the memory. There are a whole bunch of those that have. Then after you do the segment mapping, then you get to the 4-level page maps. There are the 4 levels of page mapping there, 1, 2, 3, 4, boom, then you finally get an address, okay? So the act of just getting an address is a very many multi-step process. It's very hard work. These tables are memory resident, so the actual state of the program is extremely large. Okay. So when you think you've got a 5-line program, you don't have a 5 or a 10-byte program. There's no such thing. And once you've loaded it on an operating system, you're going to have kilobytes of data even for just the tiniest program. Even a few lines, you're going to have kilobytes, tens of kilobytes of data to set the machine up and to get it ready to run. You just can't do it without it because there's so much state in here that you have to set. Note also there are 4 different privilege levels. Okay, and the privilege levels can vary depending on whether you're doing a read of an instruction or a read of a piece of data. So, immensely complicated machine. And so this is the truth, more like the truth. But even this is a simplified diagram. Just some things we cobbled together, stealing diagrams out of Intel's manual. Now, we have 2 models. One is an ISA level model, which is kind of simple. It's the thing the programmer thinks that they have, 64-bit ISA, 32E mode, 121 instructions, 223 opcodes, all of these modes. Specification of the paging, user level segmentation. You can execute it, so you can just dump your code on it and run it. It took about a minute, up to 3 minutes. Has 2 modes of operation. Now we can make it specialize it to a programmer one, so you can verify your user level programs, the kind of stuff that dumps out of compilers, or you can put it all the way in full system mode. Basically, put it in you put it in supervisor mode, and then you see everything. Okay, and it's a very complicated thing. We've done proofs in both worlds, and so I'll mention those quickly. So the programmer level allows verification application programs, assuming that the services are reliably provided. So we have a model that you can, for function calls that you would normally see in into an operating system like read, write, open, close, so on, included in this level of the model. So it's what a programmer sees, this nice linear, beautiful 64-bit address space, and reads and writes and other kind of things. Now these things are, from the perspective of this user level program though, the system calls are non-deterministic. It's not clear what you'll get back. Although if you run it, it will actually, we can set it up so it will actually call through into the underlying operating system on which this system being emulated is hosted, and actually you can read and write files and do things like that. So you can actually run the binaries that you would run on the machine directly on our model and get the same answers, bit for bit. That's the point. Okay, so here's some code. So this is a dumb little example, but just meant to be illustrative. Take the binary code produced by LLVM for a word count program. Here's some of the binary. I won't try to read it to you, but it's got like 55, 4B, 8, 9, B5, so on. I can read most of those now and tell you what they are, what instructions you see, what problems you get into when you think about this stuff. And here's a little spec. It's not actually in the format that we write it. We write it in ACL2, but I'll just kind of read it. It's if you either at the end of the string or your offset shows that you're still within the string, well, then if you read into file, then return the count that you have so far. Otherwise, add 1 to the count, mod 2 to the 32nd, and then recursively call this specification again. So this is just a stupid character counting program. This is one thing with the word count WC program, if you've used it under Linux or Unix, which counts words and lines and characters in your file. Just kind of silly thing, okay? But what's nice about the proof, when we did the verification, it also shows that no memory was used that wasn't intended. It's just confined to its area. The stack and code remain disjoint, so there are no ways that you can do any kind of malfeasance with this. There's no sequence of inputs you can put in that will cause this to fail or do something it shouldn't. And irrespective of the input size, the program uses only a finite amount of memory. These are things that you'd like to know about your program in addition to its correctness. Okay. So the system level model, this is where the whole thing's turned on, where all those tables that I showed you a couple of charts before are in play. Well, they're always in play, but I mean, now you're going to get to use them. And so the actual 52-bit address space, that's the largest physical address space that's defined for x86 to this point. It's limited by the page table sizes and just the way it is. Even though you think you've got 64 bits, you can't actually realize that physically, although you could maybe in virtual setting. And so this mode includes all the memory management mechanisms, paging structures, segments, mappings, and so forth. And again, here's a somewhat simplified version of the way paging works, or segmentation. First, you have a segment selector and a 64-bit address, and the addresses are actually 80 bits on x86. You may not realize that. And then they, you use these 16 bits to go in and get a particular segment descriptor that you want, and that puts you somewhere in this large linear memory. And then you have an offset that comes from this effective address into the linear memory. If this part's turned on, then that depends what registers you're using. In 64-bit mode, most people don't use it. And actually, for 4 of the 6 segment registers, it's no longer mapped that way. It's another side story. Anyway, after that, then you get into the actual 4-level pages where you have the CR3 register that tells you where the first, and this is a hierarchical set of page tables. You see this one first, and then it says a subsidiary one, and a subsidiary one, and a subsidiary one, and finally you get actually a 4K page. If you want 2 megabyte page, you just don't use that table, and then you just get out of here. Okay, you cut out early, so you would then only map through 3 levels of page tables. So we proved that during paging, multiple translation of a specific linear address actually produces the same addresses. You might not think that's such a great property, but actually it shows all our machinery is working, and actually the real hardware maps addresses usually twice because it wants to make sure that the map's going to work first, because then it's going to go up and update the bits, which ours does anyway. As it passes through it, it has to make these same couple of maps because you're going to change the access and the update bits as you go through the page tables, and so all that stuff has to be recorded correctly and accurately, because otherwise you will get inconsistencies when you went to look at what page tables were actually, or what pages have actually been changed. You actually go and look in the page table mechanisms, which are in the translation website, but it doesn't matter. Anyway, let's see. This is surprisingly complicated, and establishing properties about translation mechanisms is essential if you're going to prove the correctness of the actual code that maps your addresses to your programs. Otherwise, you don't know what you're doing. You're just wandering around in a big space. So, I'm down to my last slide, even early. This is an opinion now. So that's it. For coming, I get to give 30 seconds or 1 minute of opinion. What does the future hold for us? Okay. Could we imagine that that we could mechanically mechanically verify, meaning check, an x86 implementation with 10% in quotes of the performance of a commercial design? Okay, completing it. We've done it on simpler microprocessors and even physically manufactured them. About the time I think PROCOS started in 1990, we had a physically manufactured 32-bit microprocessor for which we had a correctness proof down to the gate. And then we manufactured it, we tested it for a couple of years and never found an anomaly. So it's possible that was a much simpler design. Okay, could you imagine an operating system application with 10%? Again, I don't know how to measure it, of the complexity of today's system. Could we do this? If the answer is no, then we're just definitely will not have trustworthy components, okay? So if we just are ready to give up now, meaning the answer is no, okay, the answer is no, we're done. All we are then is in the risk mitigation business as computer scientists with a formal bent. But if it's maybe, well then, we need to remove the legal impediments to allow the free, in my opinion, the mathematically accurate exchange of hardware and software specifications and their corresponding proofs, so we can all share them and know what we're using when I use a server library or something like that. That's what we got to have. And it's, I think, more of a legal problem almost than a technical one. But anyway, I thought PROCOS was ahead of its time, and I hope that you re-energize your project. Thank you.
Thank you very much. Other questions?
Well, good. I'll let you answer.
Yes, question in the back.
I'm going to take you back. Excuse me. I'm going to take you back to the hardware verification. You said they had a very good systematic process in there. When we started driving with seatbelts, we drove faster. Do you sense their process is changing because they know your verification is on the side?
Oh, yeah. They have, first thing they did is they threw out $3 million worth of tools they're releasing every year and replacing with ours. Now, that took a couple of years for them to get the confidence to do it, but yes, definitely, they're driving faster. They're trying things because we can recheck, if they come to us, we can recheck it in an hour or minutes, depending on the circuit. And so, yeah, they're trying anything now because we'll catch them out. So, pedal to the metal.
Okay, thank you very much, Warren. That's the remote report. Yes, I'm very, very pleased now to introduce Jay Moore, who everybody knows, I'm sure, who will be now giving our final talk for today on managing large terms. Jay.
Thank you, David. And thank you all. Thank the organizers especially. It's been, it's really neat to see all these old familiar faces. I'm sorry for that half of the room. Unlike Warren, I'm not going to wander over there because I'm cognizant of the camera. So I'm going to just point to this screen. It's too bad that we have this bifurcated room. I'm going to give a talk that is only illustrative of the kinds of work we do with ACL2, not the applications, which Warren was talking about, but inside of ACL2 itself, or just beyond the ACL2 where we're using these extensibility features. This was a diagram that we drew back in when the Clink stack was created, and this is the representation of the fabricated device upon which it ran, and this is the stack that included, the formal net list of this device, a machine code interpreter, an assembly language, an assembler, linker, and loader, and then a higher level language that was connected by a compiler. And there were then other things above that, including a few simple applications. And as I mentioned this morning, it was all verified all the way down with the same system. And each of these things was formalized with an operational semantics. That application was all done in the earlier version of the so-called Board-Moore theorem prover in QThelm. And at the same time, we were doing other proofs, like, for example, there was a model of the Motorola 68020, and we did a proof of the Berkeley C string library by compiling it with GCC down to the 68020 machine code and verifying it. That was being done within QThelm. And all of these applications motivated the creation of ACL2, partly as a flexible automatic theorem prover, but also as an efficient and widely used programming language, because what we began to see was the people doing these kinds of applications were writing some fairly serious programs in the logic to execute as part of these proofs. And we needed, in QThelm, Boyer and I had written a compiler. And what we wanted to do was to be able to exploit all the good work that other people were doing on compilers. And so we threw away the logic of in QThelm and adopted the applicative subset of Common Lisp, and then made our axioms consistent with Common Lisp, and then wrote a theorem prover for that. And ACL2 has evolved. That was in August of 1989, when Boyer and I started with a blank screen and started coding ACL2. And the theorem prover we're using today, the one Lawrence mentioned, is ACL2. But now, instead of Boyer and me, it's Matt Kaufman and me, with the help of a large community. Now, what am I talking about now? When you use an operational semantics to model programs, you typically have a term that represents a state. And if you then drive that operational semantics through a piece of code, you get a state expression that represents the final state of that code walk. I'm assuming here straight line code, but if it has loops, then you get a recursive function with states in it. And those expressions kind of look like this. In this version of the language, this I is the state component that holds the instruction counter or PC. S is the state component that holds a status word, and R is references the memory at an address and a number of bytes. So, for example, starting with an initial state, if you bang, every time you see a bang in front of one of my symbols, it means this is the set operation, and the access operation is the same thing without the bang. So for example, this means set the contents of the byte that's at address 4280 and going for the next 8 bytes, so that to the sequence of 8 bytes you extract somehow from the number 999. And I won't go into how you extract bytes from a natural number or in which order you write them, but there has to be some consistency there. And so you do that right, and then you do this right, and then you do that right, and then you do this right. And then you set the status word to nil, and you set the program counter to 6, and that's a symbolic state. And then if you, what I've done is just tabulate it so that the rights all have an address written in a column, so it's easy to see. And the ends are always 8 in these examples, because I'm focused right now on a model where you're only dealing with quad words, 8 byte quantities. But I'm going to generalize this to arbitrary sizes. And the accessors and change operations on states already work on arbitrary sizes. So I is the function that accesses the contents of the instruction pointer in a state. And so I applied to this term is 6, that's 6. And S applied to that term is nil. And R, reading from byte 16 and the next 8 bytes gives you, well, it would give you this, except it only gives you the 8 bytes worth of it. So in fact, it gives you the logend of X and Y mod 2 to the 64. And those are typical kinds of things you do when you're symbolically evaluating a program. Now, what about this? If you want to read from address 4280, a quad word at that address, well, there is where we wrote that quad word, and we wrote 999. But that's true only if you can get past this assignment. Because if it turns out that I is such that 40 plus 8 times I is equal to anything between 4280 and 4287, then when you do this read, you'll get something that's been affected by that right. Okay, so when you try to do this read, you have to, in order to walk past each address, you have to check that the address, the interval that's being read is independent of an interval that's being written. Now, the way we were doing proofs, in fact, the way we still do proofs for machine models like this is with rewrite rules. And so you typically might have a rewrite rule that says if you get the instruction pointer out of a state where you've set the status word to V, it's the same as getting the instruction word out of the original state, never mind the set. And if you read from address A after writing to address B, then it's the same as reading from at A in the original state, provided B plus K is less than A, or provided A plus N is less than B. I mean, these two rules go together and are what we call read over write rules. And those conditional rewrite rules suffice to do simple manipulation of code and symbolic expressions, provided the expressions aren't too deep and the expressions A, B, N, and K are not very large. Because, for example, if this is a conditional rewrite rule and you're trying to apply it, and you see an R of an A against a bang R of a B, then in order to make this simplification, you have to relieve this hypothesis. And if A, N, and B are large expressions, then you suddenly are challenged with a large arithmetic problem. And you may have to do that thousands of times if the nest of R's is deep. And that's what this talk is about. So here's the state expression I showed you originally. And in terms of size, I think of this as something about size 9, because that's the number of function symbols that appears in this expression. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 symbol function applications in there. And the biggest address or value expression I see is this one right here, which has 2 function symbols in it. So that's how I measure the size of a state. Now I'm currently working on a piece of code. It's 15,000 instructions in a formal ISA. And one of the states I'm dealing with has a little over 2 million function applications, and the biggest address or value, it has 147,000 function symbols in it. So if I were to try to backchain to this disjunction, either the write address is below the read address or vice versa, for every pair of addresses in a state like this, I would be hosed. And that's the question. How do I manage to manipulate these large states? So the key ideas were to, first of all, write a function that, and here I'm writing in ACL2, which is the common list. Write a function that by syntactic analysis creates an arithmetic interval containing the value of an arithmetic logical expression. Secondly, write a function to search a given state expression for the assignment given to a given address expression. And both of these functions deal with the quotations of terms, okay? That these functions take a constant, an object that is purportedly a term and yields, in this case, an interval, and in this case, another term, which is allegedly the assignment to that address of in a state expression. The third key idea is to hide state expressions from the rewriter so that the rewriter does not actually go into these huge states. Then combine all of this into hand-coded simplifiers for access and change expressions on states. And then finally, prove those functions correct so that they become part of the logical machinery. So basically what I'm doing is writing simplifiers for state expressions and proving them correct so that they can be used on these bigger states. The interval analyzer, by the way, I'm going to now talk about each of these very briefly. The interval analyzer, I call it ANI, and it stands for Abstract Interpreter for Natural Number Intervals. So here's a given state, here's a given expression. And if I put a quote mark on the outside of that, it becomes the quotation of an ACL2 expression. And I can think about the evaluation of that expression in an environment in which variables have values. And ANI will take that expression, the quotation of that expression, and report that the value of that expression under any assignment is allegedly lies in the interval between 288 and 536. And it's pretty easy. This thing is bounded by 2 to the 64. It's a natural between 0 and 2 to the 64 because of that 8. The shifts it down to 2 to the 61. It's really 2 to the 61 minus 1, and that's 2 to the 64 minus 1. But that log n just throws away everything except 5 bits worth, and then you multiply that by 8, and you add it to 288, and that's how you get the 536. But ANI is given also the context that the theorem prover sees when it looks at this term, because this term occurs in some formula, and that formula has hypotheses, and ANI gets those hypotheses too. And if it can find a hypothesis that says that this right here is less than 24, then the interval reported will be that. So you get the idea of what ANI is doing. Furthermore, ANI is really pretty fast. I can take the largest value term encountered in one of these typical expressions and compute the interval that contains it, that contains its value in about 1/100 of a second. So ANI is much faster than trying to pose to the arithmetic problem, the arithmetic decision procedure, prove that this lies in a certain interval. Furthermore, ANI created the interval as opposed to being given the interval and proving that it's correct. Then finding assignments uses this interval analysis. So for example, if I've got a state, my standard state expression here, and I'm looking for 4280, then of course syntactically I can just skip over the I, because if you read after writing the instruction counter, it doesn't affect the memory. And similarly for the status word. But now here, you see I'm carrying down the interval containing this, which is that interval right there. And I know that I can compute the interval for that, which is this. And they don't intersect, so I can step over that one. And then I compute the interval for that, and they don't intersect, so I get to here. And now I can compute the interval for this if I happen to know, for example, that I is less than 16. Then this expression lies in that interval, and that doesn't overlap this interval, so I can move past that. And these are the same, and so I report not just in the same interval, but they're literally the same expression. And so I can return the 999. So in general, find assignment, which is the function I just described, it returns 4 results. first of all, whether it found an assignment, and if so, at what depth. And the reason I need the depth is so that I can delete that assignment to simplify the expression if I'm overriding it with a new value. Whether the address I found was syntactically identical or merely equivalent. Any hypotheses that I might need to ensure equivalence, and the value assigned to that address or the bottommost state expression if I didn't find an assignment. And you'll kind of see how these all fit together. But basically, find assignment is the workhorse that takes an address expression and a state expression and returns a value and this other information. Now, to hide terms from the rewriter, ACL2 has a construct called hide, and hide is just the identity function. But it's treated very specially by ACL2's rewriter, and when the rewriter encounters hide of any term, sigma, it doesn't beta reduce it or rewrite sigma, it just stops and returns it. So if you have an expression and you don't want the rewriter to touch it, you hide it by putting a hide around it. And if you need to prove something about hide, you have to force the rewriter to open up that hide, and you do that with a hint. So another feature of ACL2 that I'm using is actually a feature of MQThumb, but we have an elaborated version of it in ACL2, which is metafunctions. A metafunction is just a function in ACL2, in Lisp, such that it maps the quotation of an ACL2 term to the quotation of a term with the same meaning under eval. And ACL2 can prove that. So if I define a function that transforms quotations of expressions to quotations of expressions, and I can prove that the eval of the input is equal to the eval of the output under any assignment to the variables, then that's a metafunction. And once ACL2 has proved that f is a metafunction, and the user has claimed that that metafunction rewrites functions and expressions that start with a given function symbol like capital F, then it just builds that function, little f, into the rewriter and applies it to the internal form of the expression, knowing that it's sound. It's going to do an equivalent preserving transformation. And metafunctions can look at the contextual information. So for example, what I've done is written a metafunction for bang R. So imagine that this is a state that's been hidden from the rewriter. And this is a new bang R expression with an address and a byte size, a word size, a value, which might have some hides in it. And then this is the state expression. What I want to do is simplify this. And so what happens is, first, the metafunction strips off that hide, this hide, and it strips off any hides that appear in there. And then it uses find assignment to note that this address is the same as that address and nothing gets in the way. And then because it knows the depth of this expression, it drops it and gets that. And then it puts a hide on the top of it. And that becomes a state that's now back in normal form. And so it's hidden from the rewriter. Remember, this could be gigabytes, and has been. There are no shadowed writes in it. The most recent write is at the top. I have considered putting this write down in some logical order by ordering the writes by address, but it's really faster to keep the writes at the top, the most recent writes, because programs tend to read from the places they recently wrote, and this makes it faster to find the assignments. And if someday a program, looks at something written at the very beginning, then if it writes to that, it'll drift back to the top. So this is kind of organized like a cache. And there was no theorem proving involved in this transformation. This was all syntactic. Of course, it's been proved correct. By the way, meta bang R, which is the meta function I'm talking about, actually involves 74 other user-defined functions and about 1,400 lines of Lisp okay, to do what I just said, including the interval analysis. Which, and by the way, the interval analysis handles, plus and times and log n and log or and log xor and log ior and ash and all the standard logical arithmetic that you see in a microprocessor model. For each of the accessors and changers of the state expressions, there's a meta function. And I had to prove 108 basic lemmas about access and change, and then 130 lemmas to prove the correctness of Annie and find assignment, etc. Annie, what does it mean for Annie to be correct? It means if you give it the quotation of a term, and it says it found an interval under some hypotheses, then if the value of those hypotheses under some assignment is true, then the value of the term you gave it under that same assignment lies in the interval that Annie has reported. So that's the correctness theorem for Annie. And it involves evaluation of arbitrary expressions. And find assignment is similar. And in addition to this, I used a lot of the community books in ACL2, especially a book called Tau Bounders, which supplies bounds on arithmetic expressions, and some of our arithmetic books. So using this, I can now code walk. That means symbolically evaluate a piece of code on a certain ISA. I can code walk the implementation of DES and translate the machine code into ACL2 functions. Code walk is basically an ACL2 utility that I'm developing that's comparable to what Magnus Myrene did in Hull for transforming machine code given an arbitrary ISA semantics into functions. The DES implementation I'm looking at has about 15,000 instructions in it, and it takes me about 19 minutes to code walk. Very large states are created, those ones I've referred to. Embarrassingly, ACL2 can't admit these functions because of their size. It can generate them, but then when it tries to prove that they're admissible, it blows up one of the functions and takes 686 megabytes just to print. Okay, so it takes a long time to even read in, but I don't read it because I created it in core. But in any case, as for future work, I'm in the process of generalizing to arbitrary chunks, not quad words. I have ways to make find assignment faster and smarter. I need to provide a way to prove state equality for these unnormalized state expressions, and I'm doing that with what we call a picker point strategy, which I've proved the basic limit that says two states are equal if every assignment to one is in the other and vice versa. Because now my meta functions are the only functions that ever see a state because states are hidden, I can radically change the representation of hidden states and manage the transformation inside the meta function and make find assignment faster, for example. ACL2 has hash cons and memoization thanks to Warren and Bob Boyer, and then some work by others at Centaur and me and Matt. So now it turns out I have a really good opportunity to optimize these functions by memoizing them. Something that's not a particularly valuable thing for the ACL2 rewriter itself. You might think we could speed up the rewriter by memoizing it, but that's turned out to be fruitless, at least so far, because the rewriter has so many arguments that are used to control heuristics and soft overflows and links. And then finally, and most interestingly, and typically in our work, making it possible to generate bigger states now forces us to cope with larger definitions. So we go back in and re-engineer parts of ACL2 so that I can fix this problem. I mean, why can't ACL2 admit this? I don't really know where the bottleneck is, but that's what I'm going to do when I get back to work. And this is a typical strategy in ACL2. You find a problem, you fix the problem, that creates 5 more problems for 4 to 5 years. More generally, this project illustrates a very common industrial application of ACL2, namely as a programming language for writing verified programs. And by mixing verified metafunctions with the rest of ACL2, you can build powerful domain-specific tools. And that's how the people at Centaur and Oracle and Rockwell and other places are using ACL2. There's a lot of proof, partly when they prove design's correct, but also proofs that their tools are correct. So then they can run things without doing proof, but they know they're getting correct answers. I've written a paper about this, and if it's in draft form right now, but if you're interested, send me email, and I'll send you the paper. That's it. Thank you.
Questions?
How tight are your intervals that you compute this?
They're pretty tight. I don't know how to quantify how tight they are, but for example, when I try to bound the log and, for example, I get bounds on the two pieces, the two arguments. And if it turns out that there's only 1,000,000 points, I mean, that is to say, whatever the square root of 1,000,000 is. Imagine that for example, imagine that one of them lies in an interval from 0 to 10,000, and the other one lies in an interval from 0 to 10,000. Then there's 100,000 combinations. And so I just run it. I just run log n 100,000 times to collect the largest and smallest, okay? Now, I don't do that on all functions, but I do that on certain ones where I can't analytically determine minimal bounds. And so, and because ACL2 is fast, this works. Now, we've got people who are doing a lot of SAT work in our group, and they have, there are Boolean techniques that would let me bound log n precisely without doing executions. And I'm going to be looking at that too. But at the moment, what I do is a sort of naive bound based on the bounds of the two intervals. And if I have heuristic reasons, I will do a computation to answer it as precisely as possible. But there's some other things I could try. I haven't.
Can this be understood as that here imperative programming is preferable compared to functional programming?
Well,
You can let me see
religious
what you have in this sense.
well, first of all, I'm programming applicatively. I mean, all of my code is applicative. Now, the model that's the instruction set architecture that we model with these states is clearly imperative, okay? Because we model state changes, that's the whole point. I don't particularly like dealing with imperative languages. And the only reason we do it is the whole world uses them. And so, I mean, you just have to do the problems the world wants done. But I'm actually religiously committed to functional programming and use it all the time. I mean, that's ACL2 is applicative, and all my code is applicative, and we only prove the correctness of applicative things. And we work very hard to make our applicative subset fast by suitable declarations. But
You said that we only prove applicative programs, but that's not true.
no, I mean, we only prove applicative metafunctions.
Right.
Metafunctions are written in ACL2, and they are by definition applicative, and that's what we prove correct. But yeah, as far as the applications go, we model von Neumann machines and we prove, non-applicable program. In fact, that's our bread and butter.
Okay, other questions? Rosalind?
This isn't a question so much as a comment or congratulations to Jay. Not everybody in the room may know that Jay is a kind of an honorary citizen of Edinburgh University Department of Informatics, and Jay has just been elected